Gas sensors stationed at Norris Geyser Basin transmitted data that triggered automated alerts across 3 monitoring agencies. Sulfur dioxide concentrations had spiked to 420 parts per million, triple the normal background levels. Within hours, aerial surveys confirmed the signal extended beyond Norris, elevated SO2 readings across a 15-kilometer radius encompassing Roaring Mountain, Gibbon Geyser Basin, and approaching Mammoth Hot Springs. By November 15th, total daily sulfur dioxide flux from Yellowstone measured at 680 tons, 7 times the typical 100 tons per day baseline that's been stable for decades. By December 1st, 2024, sulfur dioxide emissions had declined from a peak of 720 tons day to 380 tons day, still nearly quadruple baseline but trending downward. The rate of decrease was gradual, roughly 20 tons day reduction per week. Ground sensors at Norris showed concentrations dropping from 420 ppm peak to 180 ppm. New fumaroles continued venting but at reduced intensity. Seismicity declined to 20 to 30 earthquakes per week compared to 80 to 100 during peak activity. The helium-3 enrichment persisted, suggesting the magmatic source remained active, but degassing rates were decreasing. The system was stabilizing, though stabilizing at levels well above the pre-November baseline. Scientists interpreted the pattern as an intrusion that had reached equilibrium. A pulse of basaltic magma, likely 0.01–0.02 kilometers thupides in volume, had intruded to 7 to 9 kilometers depth in early November. Initial volatile release was vigorous as fresh magma degassed and heated surrounding hydrothermal systems. Over subsequent weeks, gas release slowed as 1. Volatile-rich magma depleted dissolved gases. 2. Permeability decreased as fractures sealed with mineral precipitation. 3. The intrusion began crystallizing, reducing gas mobility. The intrusion wasn't withdrawing, it was transitioning from active degassing to passive cooling. Whether it would remain at depth or resume activity was unknowable. Gas monitoring remained intensified through December. Daily COSPEC surveys continued. Soil CO2 surveys expanded to map degassing zones comprehensively. Helium isotope sampling frequency increased to twice weekly. Satellite thermal monitoring tracked heat flux changes. Every measurement is added to the growing dataset characterizing the episode. By mid-December, Yellowstone's gas emissions had been more thoroughly documented than ever before in its monitoring history. The data would inform understanding of caldera degassing processes for decades, but it couldn't predict whether this episode was concluding or merely pausing. Volcanic gases are direct samples from inaccessible depths. While we can't drill 8 kilometers into a magma chamber, gases that escape carry chemical information about conditions there: temperature, pressure, composition, and volatile content. The November episode revealed Yellowstone's magma system is actively connected to deep mantle sources. He3 evidence is basaltic at depth, isotope signatures, and has pathways for gases to reach the surface, permeability. This information constrains models of how Yellowstone works. The magma chamber isn't a static reservoir of old crystallized mush. It's periodically recharged by basaltic intrusions from below, which heat the overlying rhyolite, release volatiles, and drive the caldera's restless behavior. But gas data alone can't predict eruptions. High gas flux can precede eruptions, as at Rabaul 1994, Pinatubo 1991, or occur independently for years without eruption. Mammoth Mountain since 1990, Campi Flegrei ongoing. The relationship between degassing and eruption depends on magma ascent rate, volatile content, permeability of overlying rock, and whether gas escape reduces or increases eruption potential. November's surge at Yellowstone in isolation doesn't indicate imminent eruption. Combined with other monitoring data, seismicity, deformation, and thermal changes, it contributes to a holistic assessment. But gases are one piece of a complex puzzle, not a definitive answer. Based on historical patterns at Yellowstone and global calderas, the November gas episode increased eruption probability modestly but not dramatically. Baseline annual probability of Yellowstone eruption any size, approximately 1 in 730 for small events, 1 in 730,000 for super eruption. Post-November assessment, perhaps 1 in 500 for a small eruption within the next year, a slight increase reflecting elevated unrest, but still low in absolute terms. The gas surge, while significant scientifically, doesn't transform Yellowstone from safe to dangerous. It transitions the system from dormant baseline to elevated baseline, a state that could persist months, years, or decades without erupting. Approximately 40 to 50 volcanoes worldwide are degassing at elevated levels at any given time. Most won't erupt. Persistent degassing is characteristic of open vent systems like Stromboli, Etna, and Masaya volcanoes that release gases continuously for decades without major eruptions. Yellowstone, with its massive magma reservoir and extensive hydrothermal system, has an enormous capacity to degas without erupting. the November episode fits within normal variability for restless calderas. It's noteworthy for Yellowstone's recent history, but not unprecedented globally. Living near active volcanic systems means accepting that elevated activity is normal, not necessarily precursory. Gases revealed that magma moved beneath Yellowstone in November 2024. A basaltic intrusion released volatiles that escaped through fractures, increasing surface emissions sevenfold. By December, degassing declined as the intrusion equilibrated. The episode demonstrated Yellowstone's magma system is alive, periodically recharged from depth, and capable of rapid changes in behavior. It did not demonstrate imminent eruption. Most likely outcome, gases continue declining toward baseline over the coming months, seismicity returns to normal, and the intrusion crystallizes at depth without reaching the surface. But certainty is impossible. The invisible gases told us something moved below. What happens next, only time will reveal. What you cannot see can still be measured. What you cannot touch can still be sampled. Sulfur dioxide, carbon dioxide, and helium-3 invisible exhalations from Earth's interior revealed that Yellowstone's deep magma system stirred in November 2024. The gases peaked, then subsided, carrying chemical messages about processes occurring miles underground. Scientists decoded those messages through instruments and isotopes, learning the mountain's secrets one molecule at a time. The gases have spoken. The interpretation is clear. The future remains uncertain, and the monitoring continues, one breath at a time. Volcanic gases are invisible messengers from the deep Earth. They originate in magma chambers miles underground, carrying chemical signatures that reveal what's happening at depths humans can never directly observe. Sulfur dioxide only exists in a volcanic environment. It's unambiguous evidence of magmatic activity. When SO2 concentrations increase suddenly, it means one of three things. New magma has arrived at shallow depth and is degassing, existing magma is releasing volatiles more vigorously, or permeability in the rock above the magma chamber has increased, allowing gases trapped for years to escape. All three scenarios indicate the volcanic system is changing. But sulfur dioxide wasn't the only anomaly. Carbon dioxide sensors in soil across the caldera recorded increases from 300 ppm background to 850 ppm in localized zones. Helium-3, a primordial isotope from Earth's mantle that only reaches the surface through volcanic systems, showed concentration ratios increasing by 18% above baseline. The helium-3-helium-4 ratio is particularly diagnostic. High helia-3 means fresh magmatic contribution from the deep mantle. Combined, the multi-gas signature painted a clear picture. Something deep beneath Yellowstone was releasing volatiles, and those gases were finding pathways to the surface. Magma is not just molten rock, it's a solution of silicate melt with dissolved gases held under immense pressure. The primary volcanic gases are water vapor, H2O, typically 60 to 90% of total gas, carbon dioxide, CO2, 10 to 40%, sulfur dioxide, SO2, 1 to 10%. As magma rises and pressure decreases, gases exsolve like opening a carbonated drink. This degassing can drive volcanic eruptions, or gases can escape through permeable rock without erupting.
Each gas tells a different story. Water vapor escapes easily and early. It's the first to exsolve as magma rises. Carbon dioxide exsolves at greater depths than water because it's less soluble in magma. Sulfur dioxide is intermediate, degassing primarily at shallow depths 1 to 5 kilometers. Helium-3 is the deep trace. It comes from the mantle and only reaches the surface when there's a direct connection to deep magma sources. By measuring the ratios between these gases, scientists can estimate the depth and volume of degassing magma, whether it's rising or stagnant, and whether it's fresh basalt from the mantle or recycled rhyolite that's been sitting shallow.
Yellowstone releases gases constantly. It's one of Earth's largest sources of geogenic CO2, emitting approximately 45,000 tons per day under normal conditions. This background degassing comes from the massive magma system, 46,000 cubic kilometers of partially molten rock, steadily releasing volatiles even though no eruption has occurred for 70,000 years. The sulfur dioxide baseline is much lower, around 100 tons per day, because most sulfur stays dissolved in magma until it reaches very shallow depths or erupts. When SO2 suddenly spikes sevenfold, it's geologically significant. It means gas release mechanisms have fundamentally changed. The November 14th spike wasn't transient. Between November 14th and November 26th, sulfur dioxide emissions remained elevated, fluctuating between 580 to 720 tons per day. Ground-based COSPEC correlation spectrometer measurements performed by driving beneath volcanic plumes and measuring absorption of ultraviolet light by SO2 confirmed the airborne data. More troubling, the gas release was accelerating at specific sites. Roaring Mountain, historically a fumarole field releasing modest amounts of steam, showed SO2 concentrations reaching 1,200 ppm locally, levels that required closing hiking trails due to respiratory hazards. New fumaroles opened. Between November 15th and 20th, 6 previously inactive thermal features in Norris Geyser Basin reactivated, venting sulfur-rich gases. One opened in a boardwalk area, forcing emergency closures and rerouting of tourist paths. Trees near active vents showed acid-damaged needles browning from sulfuric acid aerosols, forming when SO2 combines with atmospheric moisture. The landscape was responding to subsurface changes in real time. Park geologists documented ground temperatures increasing 15 to 20 degrees in areas adjacent to new vents. Something was injecting heat and gas into the shallow hydrothermal system. Gas releases don't occur in isolation. Concurrent seismic monitoring detected 180 earthquakes beneath Norris Geyser Basin between November 10th and 26th, with magnitudes 0.8 to 3.4. The earthquakes clustered at 3 to 7 kilometers depth, exactly where geophysical models position the top of Yellowstone's hydrothermal magmatic transition zone. The pattern suggested rock fracturing, opening pathways for gases trapped at depth to escape to the surface. Whether the fracturing was driven by magma pushing upward or by thermal stress from heated fluids remained ambiguous. But the temporal correlation between earthquakes preceding gas increases by 3 to 5 days suggested a causal relationship. The critical question, was the gas surge magmatic new magma degassing or hydrothermal old magma's gases finally escaping through newly opened fractures? Scientists analyzed the multi-gas ratios for clues. The helium-3, helium-4 ratio increase of 18% suggested fresh magmatic contribution. Helium-3 only comes from active mantle sources. The CO2-SeO2 ratio, measured at 15.1, indicated shallow degassing. Deeper magma produces higher CO2-SeO2 ratios. The sulfur isotope composition, dead Duke-Feeb 4S values, matched Yellowstone's known magmatic signature, not hydrothermal alteration products. Combined evidence leaned toward magmatic. A pulse of basaltic magma from the deep reservoir had likely intruded upward, releasing volatiles into overlying hydrothermal systems. But magmatic degassing doesn't necessarily mean imminent eruption. Magma can degas at depth without ever reaching the surface. The gases percolate upward through fractured rock, carried by hydrothermal convection, emerging at fumaroles and hot springs. This open system degassing can continue for months or years, releasing pressure that might otherwise drive eruption. In some cases, vigorous degassing prevents eruptions by reducing volatile content that would fuel explosive activity. The November gas surge at Yellowstone could represent either an eruption precursor or a pressure relief mechanism. Data alone couldn't distinguish. Scientists calculated the volume of magma required to produce 680 tons of SO2 per day. Assuming typical basaltic magma sulfur content, mort 0.10.2 weight%, and complete degassing, the source magma volume was approximately 0.010.02 cubic kilometers. That's small compared to Yellowstone's total magma chamber volume, 200 to 600 kilometers, the prudence of potentially eruptible material, but significant as an intrusion event. For comparison, Mount St. Helens' 2004-2008 dome-building eruption involved mort 0.1 kilometers, the prudence of magma over 4 years. Yellowstone's November intrusion, if that's what it was, represented 10 to 20% of that volume, but compressed into weeks rather than years. On November 22, 2024, the Yellowstone Volcano Observatory convened to assess whether the gas anomaly warranted changing the alert level from normal green. The data were compelling: a 7-fold SO2 increase, a magmatic He3 signature, concurrent seismicity, and new fumaroles. However, no ground deformation had been detected by GPS networks or satellite INSAR. Typically, magma intrusions cause measurable surface uplift. The absence of deformation suggested either 1. The intrusion was too deep, 8+ kilometer, to produce surface effects, 2. The volume was too small, or 3. This was primarily gas release without significant magma movement. After deliberation, YVO issued a volcanic activity notice but maintained normal alert status, emphasizing enhanced monitoring. The decision reflected volcanic monitoring's inherent conservatism. Alert level changes trigger public concern, media attention, and operational impacts for the National Park Service. Elevating unnecessarily erodes trust for future warnings, but failing to elevate when warranted risks lives. YVO's judgment: gas anomalies alone, without deformation or accelerating seismicity, didn't meet advisory criteria. But the situation was ambiguous enough to warrant public notification and increased surveillance. Daily gas monitoring increased from weekly to continuous. Additional SOSPEC surveys were scheduled. Satellite thermal monitoring intensified. The watch was on. The National Park Service closed high-risk areas, boardwalks within 500 meters of new fumaroles were blocked. Roaring Mountain Trail closed indefinitely due to SO2 concentrations exceeding 5 ppm, the 8-hour occupational exposure limit. Rangers distributed health advisories about volcanic gas exposure. Symptoms include eye irritation, respiratory distress, and headaches. Visitors with asthma or respiratory conditions were warned to avoid thermal basins on high gas days. The park remained open, but the experience changed: more restrictions, more warnings, and heightened awareness that the thermal features aren't just tourist attractions, but active volcanic phenomena. Yellowstone's instrumental gas monitoring began systematically in the 1990s, but historical records describe unusual degassing episodes. In 1971, before continuous monitoring existed, scientists documented increased fumarole activity at Norris, coinciding with seismic swarms. In 1985, new vents opened near Roaring Mountain, releasing sulfur-rich gases that killed vegetation in a 50-meter radius. The 2004-2009 uplift at Norris included gas flux increases, though quantitative measurements were incomplete. The November 2024 episode was the best documented gas surge in Yellowstone's history, but not the first. The pattern suggested episodic intrusions from the deep reservoir periodically inject volatiles into the shallow system. Other volcanoes provide comparative context. Mammoth Mountain, California, experienced CO2 releases in the 1990s that killed over 100 acres of forest and created ground gas hazards that persist today. The gas came from basaltic magma intruding beneath the mountain, an intrusion that never erupted but fundamentally changed the hydrothermal system. Campi Flegrei, Italy, shows cyclical degassing correlated with bradyseism, ground uplift/subsidence. Elevated gas without eruption is common at restless calderas, but Rabaul, Papua New Guinea, showed increasing gas emissions for months before its 1994 eruption. Degassing can be an eruption precursor or a standalone event, distinguishing which, in real time, is volcanology's central challenge. Volcanic gas monitoring employs multiple techniques, each with strengths and limitations. Ground-based sensors at fumaroles provide continuous data, but only at specific locations. COSPEC and FlySpec instruments mounted on vehicles or aircraft measure SO2 flux across entire volcanic plumes by analyzing ultraviolet light absorption. Multi-gas instruments simultaneously measure SO2, CO2, and H2O ratios in real time. Soil gas surveys map CO2 emissions across landscapes using portable sensors. Satellite instruments like OMI, Ozone Monitoring Instrument, detect large SO2 plumes from space. Each technique captures different aspects: continuous versus synoptic, single point versus integrated, ground level versus atmospheric. At Yellowstone, the integrated approach detected November's anomaly from multiple independent methods. Ground sensors at Norris triggered first. Aerial COSPEC confirmed elevated flux basin-wide. Soil CO2 surveys identified expanding degassing zones. Satellite data, while less sensitive for moderate SO2 emissions, showed atmospheric SO2 concentrations above detection limits on November 18th, rare for Yellowstone, which typically doesn't produce plumes large enough for satellite detection. The multi-method convergence provided confidence that the signal was real, not an instrumental artifact, and widespread, not localized. Advanced geochemical techniques provide deeper insights. Helium isotope Tharkphi-39 extinguish mantle sources. High Tharkphi-39 Tharkphi-C reveal whether CO2 comes from magma, sedimentary rocks, or biological processes. Sulfur isotope Tharkphi-39 sedimentary rocks or biological processes. Sulfur isotope Tharkphi-39 citing magmatic versus hydrothermal sulfur sources. Yellowstone's November samples showed Tharkphi-39 as 16 times atmospheric, definitively magmatic, and mantle-derived. Carbon isotopes indicated magmatic CO2, not limestone dissolution. Sulfur isotopes matched known Yellowstone basalt signatures. Every geochemical test pointed toward fresh magmatic volatiles, not recycled hydrothermal gases. For residents of gateway communities, Gardner, West Yellowstone, and Mammoth Hot Springs, volcanic gases are normally imperceptible. Tourists visit thermal basins, photograph geysers, and leave unaware they're breathing volcanic exhalations diluted to harmless concentrations. But November 2024 made gases tangible. Some Gardner residents reported sulfur smells on high gas days when winds carried emissions from Mammoth Hot Springs. A few individuals with respiratory sensitivities experienced symptoms. The invisible became noticeable. For many, it was the first time the volcanic nature of the landscape felt real, not abstract. Public health officials issued advisories but emphasized context. Even at 680 tons a day, Yellowstone's SO2 emissions are small compared to industrial sources or volcanic eruptions. For comparison, Mount Etna releases 3,000 tons of SO2 daily during normal activity. Kilauea, during its 2018 eruption, emitted 30,000 tons a day. Yellowstone's November surge was noteworthy for Yellowstone, but not extreme globally. Ground-level concentrations remained below EPA health standards, except in immediate fumarole areas already closed to the public. The risk was primarily to those spending extended time near active vents, park staff, scientists, not casual visitors. Tourism showed mixed responses. Some visitors canceled trips citing health concerns despite the actual risk being minimal for typical park visits. Others were drawn by the novelty of experiencing an active volcanic event safely. Overall, November visitation declined 8% compared to the previous year, modest but measurable. Hotels in Gardner reported a 12% cancellation rate for late November bookings. Tour operators offering thermal basin tours saw a 20% decline. The economic impact was real but not catastrophic. The broader lesson: perceived risk often exceeds actual risk, and public perception is shaped by media narratives as much as official communications.